I'm Bhavithir Bhardwaj. Welcome to episode 8 of Genesis of Tomorrow. The following is a conversation about physics, quantum mechanics, cosmos, and more with Mr. Flynn Linton, an enthusiast in the domain of theoretical physics with his master's in particle physics at ETH Zurich. Also, 86.1% of you watching this have not subscribed yet. If you get even the slightest bit of value from our show, please support us by clicking that subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. Enjoy and thank you. Before anything else, I would like for you to set a precedence in regards to the basics of theoretical physics. And I feel the best approach to that would be to start by introducing the concept of the standard model of particle physics, what it is, and why is it important in the first place.
Well, the standard model is currently it is one of the most well-tested theories in physics, and essentially we use something called a quantum field, which is just a mathematical object that we can construct to describe the dynamics and behavior and interactions of all of the different fundamental particles that we know. So by fundamental particles, what I mean is ones that can't be broken up into smaller particles. It's like electrons, for instance, and quarks, which together build up protons and neutrons, which build the nucleus of the atom. And then when that's bound with electrons, it creates the whole atom. And the standard model isn't perfect; that it does have some holes in it. So it's pretty good at describing three of the four fundamental forces of nature that we know of, which is electromagnetism, so how light behaves, and the strong and the weak nuclear forces. The strong nuclear force tells us how protons and neutrons stick together, how the quarks stick together in the nucleus of an atom to form these particles. And the weak nuclear force also comes into play there, but it's predominantly responsible for nuclear decay. And the one missing piece of the standard model is gravity. So gravity doesn't it's not well described. Well, we can't describe the framework of gravity that we use in general relativity, which is our best understanding of how gravity works, within the standard model. They're two very different theories. The mathematics is very different, and how you construct them is very different. So technically, it's a very difficult thing to merge that group of ideas. But there are more fundamental problems as well that arise. The work that the work that I do is predominantly in gravitational wave physics, so it's somewhere in between the two.
So, talking a little more about that, if you look at the matter of quantum gravity itself, there are primarily two major schools of thoughts, uh, being the string theory route of or the approach to tackle this, or the loop quantum gravity. I would like for you to probably explain this for somebody who's never heard of it, stating a fundamental basis for whatever you're going to be talking about further, in which I'd like for you to take a deep dive in the mathematical essence of quantum gravity.
Okay, well, I'm actually not very well versed on either string theory nor loop quantum gravity, but the work that I have been doing is what we call a semi-classical limit of a full theory of quantum gravity. And so what that means is essentially we're studying mathematics and the behavior of of masses and quantum objects or quantum particles within a particular limit that you take of quantum gravity. So it's called the semi-classical limit, and essentially this is a limit in which the gravitational field is very weak, and so self interaction effects between the gravitational field itself are actually quite small. And so you can actually use the framework of quantum field theory, which is the mathematics used to describe the standard model, so electromagnetism and the strong and the weak nuclear forces, to get an approximation of how gravity behaves in this limit, or how a quantum theory of gravity would behave in this limit. So experimentally, if you were to test a full theory of quantum gravity, or even just theoretically, if you want to test a full theory of quantum gravity, it would need to reduce to this semi-classical limit, taking the appropriate approximations, which are when gravity is quite weak.
Right. How does this apply? Like, have you probably been studying about how this all works in regards to black holes, like the quantum side of the quantum explanation of it, and then probably the classical explanation of it?
Yeah, so in Einstein's theory of relativity, we call that it's called a classical theory. It has nothing to do with quantum mechanics. In Einstein's theory of relativity, you can construct solutions to Einstein's field equations, which are a set of equations that describe the dynamics of spacetime, which is a mathematical object that we construct to describe the bending and stretching and curvature of space when you have mass or energy appear in space. And there are sets of solutions that coincide with black holes. So you have a singularity at the center, and around that you have an event horizon past which no information can escape. And these solutions are, in general relativity, perfectly valid. They're perfectly mathematically consistent, and so there was no reason to think that these wouldn't exist. In in a quantum description of a black hole, obviously people found these classical solutions, and like in the mid 20th century, they were very interested in using quantum theory to describe black holes to potentially uncover some interesting dynamics that the purely classical general relativity wouldn't be able to produce. And this is in this semi-classical limit of quantum gravity that I was talking about before, is when Hawking and a bunch of other scientists formulated the ideas behind black hole thermodynamics. So one branch of that, for instance, is Hawking radiation. So a black hole will tend to radiate a small amount of low energy photons or low frequency light, and it'll radiate until the black hole evaporates, essentially. I have There is a partial application to black holes in what I'm doing. Um, there was a lot of work done on black hole information, so studying, whether or not information is truly lost within when it goes past the event horizon of a black hole. And obviously, information is a big topic within the field of quantum physics. There's an entire branch called quantum information. And so a lot of people were working on trying to figure out exactly what happens to this information when it crosses the event horizon of a black hole. And some of these ideas led a group at the University of Chicago in the United States to research to try to figure out what happens to a quantum state when it loses information past the event horizon of a black hole. And that's kind of where my work comes in. I'm not specifically working with black holes, although I was looking at how a quantum state will lose radiation due to something called gravitational waves, which I can discuss if you'd like.
Yeah, please, please.
So I mentioned before about this semi-classical limit and when gravity is very weak. And essentially, if you take Einstein's field equations describing the dynamics of space and how it stretches and curves, and you take the limit in which gravity is weak, so of the amplitude of gravity is very small, you get something very similar. Well, you get exactly the wave equation, which is an equation that describes the dynamics of how a wave propagates. And so naturally, that suggested that there were wave-like solutions to general relativity, at least in this limit, in the semi-classical limit in which gravity is weak. And in fact, it's been shown in the past that these are proper solutions of full general relativity as well, not just this limit that we're taking. So it's not just a consequence of this limit. It appears in the full, extremely well-tested theory as well. And essentially, a gravitational wave, you can think of it's a little bit of an abstract idea, but I think I have a good analogy for it. So imagine I throw a stone into a still pond. When the stone hits the water, it's going to create concentric ripples away from the stone that are going to propagate outwards. And if you have, say, and these are waves, they're waves on the surface of the water. If you have, say, a leaf or a lily pad sitting on the surface of the water, some distance away from where I threw the stone in, it's going to move up and down. It's going to oscillate with the waves on top of the water. And a very similar thing happens in the gravitational case. So if I have say two black holes, for instance, or other two really heavy objects, say orbiting one another, we call that a binary system, then those two objects are going to radiate gravitational energy and eventually merge into each other. And that gravitational energy is in the form of gravitational waves. So rather than the surface of the water being the medium for which this energy propagates outwards, like on the surface of the water, it's space itself is this medium that propagates this energy in a wave-like form. And so if you have say a particle some distance away from the source of the gravitational wave, so the two black holes merging into each other, when the gravitational wave passes through this particle, it's going to cause it to oscillate back and forth because the gravitational wave actually stretches and contracts the space around the particle. And so it moves just like the lily pad moves on the surface of the water. And one very interesting thing which arises in gravity, and this, by the way, has been experimentally confirmed. So the first direct evidence of gravitational waves was done in 2016 by LIGO, which is a big ground-based gravitational wave detector in the United States. Essentially, it works. It's a device called an interferometer. So you have two perpendicular arms like this that are very long. I'm not sure how long, and they send beams of light down each of those arms. And the arms are the exact same length, and they've got some of the best engineered mirrors ever made at the ends of those arms, which reflect the light back to where it came from and into a detector. Because light travels at a constant speed, the speed of light, which is dictated by Einstein's relativity, if the length of the two arms is exactly the same, one would expect that the light is detected by both detectors at the exact same instant in time. They've traveled the same distance and they move at the same velocity. However, when the gravitational wave passes by, because of the nature of general relativity, the contraction and expansion of space because of the gravitational wave actually causes the light to have to travel along a slightly longer or slightly shorter path than it would if no gravitational wave was present. And so you actually measure a very small difference in the time that it takes for the photon to arrive back at the detector, from which you can decode a lot of information about the gravitational wave. So this oscillatory behavior of the gravitational wave has actually been experimentally confirmed quite a few years ago, and there's lots of future detectors that are being planned over the next decade or so that hope to detect more things about gravitational waves that we haven't yet been able to experimentally confirm. And one of these things is called the memory effect, which is something I was working on quite closely. And if we go back to the example that I talked about, where you have two black holes that create gravitational waves, and you have a particle sitting some distance away from it that gets oscillated by this gravitational wave. Say we have two particles next to each other, far away from where these gravitational waves are being produced. These two particles, when the gravitational wave hits them, are going to oscillate back and forth like this because of the stretching and contraction of space from the gravitational waves. Not only that, but there's a very small effect called the memory effect, which tells us when the gravitational wave is hitting these two particles, they will actually slowly start to drift apart. And so when the gravitational wave passes, and you're just back to flat, empty space in the region around where these my two particles are, they retain a sort of memory of the gravitational wave having passed by because they're slightly more separated than what they were before. In the case of water waves on the surface of a pond, you would expect that the lily pad returns to the exact same position that it started out at. And a few minutes after I throw the stone in the pond, the water ripples are going to settle, and you're not going to even be able to tell that I threw a rock in the pond. And that's the fundamental difference here, because in gravity, there actually is an inherent memory of the gravitational wave having passed through it, hence the name.
Wow. Okay. Two, three things. First of all, I may sound really dumb right now, but in this semi-classical limit, this theory that you've been part of, what exactly does this limit pertain to? No, I mean, what is it the limit of, sort of? Like what criterion are we measuring in order to determine that this limit, probably taking it as a threshold, if we reach this or we cannot reach this, like what are the effects or the implications of all of it? What essentially is this limit?
Effectively, you can think of this limit as just the weak limit of gravity. So when gravity is very weak. So when you have two black holes that are generating gravitational waves, if you're very close to those two black holes, the amplitude of the wave that it forms is going to be quite large, and so there's going to be a lot of stretching and constructing of space. It's going to be probably quite violent, actually. But if you're very very far away from these black holes, it's just going to be like very weak ripples on the surface of the water. If you go very far away from where I threw the stone in, the amplitude of these waves is going to be quite small, and so you can think of this as a very small perturbation from usual flat space. That's basically the semi-classical limit that I'm talking about here, which
Right.
we measure gravitational waves in this limit because our mathematics our mathematics describing gravitational waves is done within this limit.
Another thing that came up in my mind while you were talking about this: how do these gravitational waves or the work that you're doing in the semi-classical limit, how does it change or gets affected when we are interacting with probably dark matter or dark energy? First of all, what is dark matter and dark energy? A formulative basis. And then how does gravity sort of work around with those entities?
That's a good question, and if I was able to tell you, I'd think I'd have a Nobel Prize. No, I'm not. I haven't studied dark matter in or dark energy in any capacity. It's kind of its own branch of astronomy, or astrophysics, and cosmology. To my understanding at least, most of dark matter research involves, well, a lot of dark matter research involves studying the dynamics of galaxies. So much larger scale things than like a black hole binary merger as producing gravitational waves, and also dark energy, and I think dark matter as well comes into play when discussing. It's one candidate for describing models of inflation, which inflation describes the expansion of the universe. So originally, the universe was very, very small and very hot, and it rapidly expanded. And it's not really known exactly why it's done this, but we have been able to measure through something called the cosmic microwave background, which is like a background sea of very, very low energy photons, a very, very low frequency light that we can measure. It has been confirmed that we can actually, the universe is expanding. And not only that, but the rate of expansion is accelerating. One candidate to describe that increase in rate of acceleration is dark energy, which mathematically the most simple and naive way of incorporating that into our theories describing the universe is to add another term in Einstein's equations, which drives this expansion.
What do we do not know about subatomic particles? You did mention initially when we started the conversation how the standard model has its limitations, but now, sort of explicitly talking about it, what are the major areas that are sort of undiscovered or we are trying to tackle in order to find solutions to the unanswered questions?
Well, one of the largest problems, of course, is trying to merge the ideas of the standard model with gravity. But another one is something called CP violation, which comes into play in the electroweak sector of the standard model. So the weak and electromagnetism parts of the standard model that describe those two forces, electromagnetism and the weak nuclear force. And CP violation is intimately tied to something called baryogenesis. Actually, I could be wrong on that. It's been a little while since I studied that. But baryogenesis is a very interesting topic, and it is one of the major holes in the standard model that we've not yet able to describe fully. At least we haven't been able. There are proposed models to describe baryogenesis, but there is no experimental evidence of that. So what baryogenesis is, it essentially describes the mechanism for which we have an asymmetry in the amount of matter and the amount of antimatter in our universe. So matter and antimatter, that sounds like something out of science fiction, right? When I say matter, I'm talking about pretty much everything around you, everything you can touch, my laptop, my desk, my mouse, things like that. Things that are just made out of regular atoms and molecules. Antimatter is very similar to matter, except some of the properties are slightly different, slightly reversed actually. So an electron is a particle, a matter particle, and if you reverse the charge and also the spin on the electron, well, sorry, just the charge of the electron, then you get its antimatter counterpart, which is called the positron, which is basically just a positively charged electron. And they've been able to make very small antimatter atoms, like hydrogen atoms and maybe helium as well. I'm not quite sure how that goes. Out of these antimatter constituents, so the positron, the positive electron, but also I believe they've been able to create. I could be wrong. I'm not quite sure. I believe they've been able to create uh, the antimatter constituent of a proton, which would be a negatively charged proton. And in the very early stages of the universe, something happened. We don't know exactly what. It's an open field of research, which caused far more matter to be produced in the universe than antimatter. I think it's something like 97, 98% of all of this stuff in the universe is regular, of all of the matter in the universe is regular baryonic matter, we call it. And the last little bit is antimatter. And we're not exactly sure why there's this asymmetry. It seems a little bit unnatural. Physicists, theoretical physicists, and mathematicians as well, we really love symmetry, to the point where I don't know. Sometimes it may hold us back. We like very very pretty looking equations, um, and very symmetric ways of describing things that aren't messy, because the universe is beautiful and simple. But this is obviously not. This is a very very sharp asymmetry that's been produced.
In 2012, Higgs boson was discovered. Why was its discovery so significant in our understanding of how physics essentially works?
Okay, well, up until then, it had been quite a while since anyone had discovered a new sort of fundamental particle. I don't remember exactly when the last one was discovered. I think it was the top quark. It was a substantial amount of time before then, so a lot of people were a little bit on edge, because we haven't, in the second half of the 20th century, we discovered so many particles that every man and his dog had a new particle named after him. But then we started to, find most of these fundamental particles, and the list of particles that we hadn't yet discovered had started to dry up. And in the 60s, Peter Higgs and also a couple of other scientists formulated that there's this particle called the Higgs boson, which is responsible for giving particles, fermions, like electrons and quarks, for instance, their mass, and through a mechanism called electroweak symmetry breaking. And when this was up until this was discovered at the end of 2012, it was only theoretical conjecture. It had been nearly half a century of these theoretical ideas being proposed and being used in all of our calculations, describing electroweak physics, but just the standard model in general. But we hadn't been able to actually produce this particle at a particle detector. It's like the Large Hadron Collider at CERN in Switzerland was the detector responsible for finding this. Part of the issue there was because the Higgs boson is an extremely heavy particle compared to all of the other particles in the standard model. And Einstein famously formulated E is equal to mc squared. So the mass and energy of a particle is very intimately linked. It's two of the same thing. And so a very heavy particle requires an enormous amount of energy to be able to produce that particle in an experiment. Another problem there was also that uh, its interaction is very weak compared to with other particles, compared to the interactions between other sort of standard model particles that we can produce. But yeah, it was kind of the last, or one of the last major breakthroughs in particle physics. Obviously, there have been more
Mhm.
breakthroughs since then, but this was the last time we discovered a major particle that revolutionizes our understanding of how the standard model works.
How did you get involved in this world of particle physics and the work that you do with gravitational waves and everything? You did. I mean, what was your journey from your early school days, probably? How did this inclination towards the subject matter develop?
I get this quite a lot, and I think a lot of people in somewhat abstract fields get this a lot because it's not really the general public doesn't really know what a theoretical physicist or a physicist does or a mathematician does on a day-to-day basis. And I would say if there's one thing that I've been following throughout my entire career in physics or science in general is that I've just followed my curiosity. For some people, it's easier than others. There's a lot of like, external factors that come into play there. For instance, the quality of your teachers in school, encouragement given by your teachers and your parents. I had a very good, I had very excellent physics and maths teachers in high school, especially the later years of high school, which and they really allowed me and encouraged me to explore my curiosity. And at some point you start having ideas or asking questions that you can't really explain using the physics or the maths that you study in high school. So I thought, huh, I need to go to university if I want to answer these burning questions that I have, or if I want to understand these things that sound really interesting that I have no idea about, like quantum physics and particle physics. And so I did. In Australia, which is where I'm from, there's very little research in particle physics because of the history of the field. A lot of these physicists and mathematicians that developed quantum theory and particle physics as a whole were around continental Europe, Germany, France, Austria, Switzerland, Russia, places like that. And so there's a lot more incentive for this research to have been developed in this part of the world because there's such a rich, intimate history of the field being developed here, which is, I guess, one of the reasons why the Large Hadron Collider is the big particle accelerator is located in Switzerland. And so I decided I wanted to learn about particle physics. So I came over here to learn about particle physics. And I became a little bit more interested in gravity and theoretical cosmology and early universe physics a little bit later into my degree when I got a better understanding of the state of modern particle physics. So we were talking before about how we discovered the Higgs boson in 2012, and I mentioned that it was one of the last like major breakthroughs in particle physics in terms of like particles being discovered. Major things that completely shift our understanding of how the standard model and physics as a whole works. And so, partially because of that drought of discovery, a lot of physicists in the modern day are working on precision calculations and incorporating things like machine learning into their calculations. And I don't know, for a lot of people, it is a very interesting field that to study. But for me, I really wanted to study some. I like some more pen and paper work rather than computational things, which drove me a little bit towards gravitational physics. Also, another reason why I'm interested in that is because there's quite a big future, I believe, in gravitational physics, especially gravitational wave physics, in the next few decades. I mentioned before there's some more gravitational wave detectors that are being built in the next like decade or so. One of them is called the LISA project, the Laser Interferometer Space Antenna. It's a big gravitational wave detector that they're going to launch into space. The mission is projected for the mid 2030s, and it's going to be three big satellites orbiting around the Earth that's going to be able to measure gravitational waves in a slightly different frequency and amplitude band to what we can measure here on Earth. And that's predicted to be able to measure some gravitational wave signatures that may actually hint at new physics beyond the standard model. So I really truly believe that gravitational wave physics will be, theoretical cosmology in general, will be the next major thing to drive the direction of theoretical particle physics, theoretical physics in a whole, or particle physics in general.
I'd really like to talk to you about, in continuation to whatever you have said. I Please tell me how is it? There is a very typical structure of thinking where research or pure sciences as a field is looked at something which is not very viable, not a very viable option as a career, which I feel is tremendously understating the potential of the field and just how much potent it is at large. Like researchers and I'm not talking about professors, but really just researchers, maybe in theoretical physics or experimental side of things, working at CERN or other places. I mean, please touch upon this aspect of how scalable this entire scientific industry is at large.
In medical related fields, for instance, in a lot of places you go, there's of course a lot of money because it's got a very immediate and very relevant practical application to your everyday person, be it advances in general understanding general health of people, diet or exercise, or more complicated surgeries to help save people's lives. But across the board, anywhere you go, there will be, at least in my experience, there seems to be a less urgent emphasis on understanding these more highly theoretical fields, and partially that's in good reason because the work that I'm working on, the work that other theoretical physicists and mathematicians are working on, realistically, we're not going to see practical application of these things for a very long time. And so there's no immediate urge to do that research now. But the thing is doing that research now allows for new technologies and new advances in all sorts of different fields that we never even thought were possible at some point in the future. Uh, an interesting example, actually, is the discovery of the electron. I don't remember exactly off the top of my head who it was who found the first experimental evidence of the electron, but I believe it's his paper. There's a famous line in the bottom of his paper which someone like the publisher of the journal made him take out, which was he sees no future practical use for the electron. And looking back at that now, it seems ridiculous. All of our modern infrastructure uses electricity and relies on circuit theory and all of these other things. All of quantum technology relies on very similar stuff as well. Our modern world is built on this. But going back to those days, it's very difficult to have that sort of foresight because it's really an open-ended book. You don't know where the research is going to lead. And That's one of the reasons why I think any research, practical or more theoretical stuff, is extremely valuable and should be invested in, because at the end of the day, you don't always know exactly where this research is going to lead you, what sort of practical applications it's going to be able to produce, what sort of impact it's going to have on society 5 years from now or 100 years from now.
I also feel, I haven't many people talk about this aspect of scientific research, but I feel the entire curation of whatever you do is a very creative process, probably in a different way than the creative fields, art and music and dance and etc. But still, it requires a very out of the box thinking for an individual researcher to incorporate when they've got their back against the wall, because you continuously have to deal and fight with new challenges and dead ends, and then you have to probably recalibrate your entire approach of resource that you had been utilizing, and that takes some sheer amount of creativity to just come up with different and new routes to take to probably be able to solve a singular problem in a network of umpteen different things that would finally land you to your end objective.
Yeah, you're absolutely right. A lot of people, I have fun telling this to people. A lot of people think that scientists, especially people in more theoretical fields like physics and mathematics, are not very creative people. But in fact, it's the opposite. You're using, you need to be very creative to come up with novel ways of solving problems. Even just in my thesis, there was about a month or two period where I was in a pretty serious dead end, and I had to dig myself out of that. And that's just the nature of research, because you don't know the answer. You have to kind of take a stab in the direction, in some sort of direction, and hope that something good comes out of it. It's you channel the creativity in a different way to what you do in areas that one would consider typically creative. But yeah, as you mentioned, like dance, art, drawing, that sort of thing, is not the same sort of creativity, but it kind of is. It's like a different flavor of that creativity. You need to channel it in a slightly different way. But yeah, as you said, it's extremely important to have that creativity and also the curiosity that allows you to use that creativity to drive new research, the new innovation, even in technologies.
What has worked for you personally to channelize or focus that creativity or critical thinking, or just arriving with different new out of the box approaches to things?
I don't know if I would say I had a particular strategy of doing this. In general, myself and a lot of other scientists are very logical thinkers, especially more so physics and mathematics, using a very logical, consistent approach to move from one step to the other. That's part of it, I guess. Another part of it is just sitting in a room with the problem, no distractions, and just letting your mind have the space to think about this for however long it might take. Sometimes it could be a few minutes, a few hours, or months. But
you know gi-
I think if you give yourself this time to just let your mind process things and wonder about the problem, um, then eventually things piece themselves together.
I'm really compelled to ask for your 2 cents upon social media and its influences.
Influences on what exactly?
Preventing just what you were saying is the right approach towards catering to the problem. Sitting in the room, logging yourself with the problem and nothing else.
So, just like just about everyone else my age, I'm victim to social media. It's very difficult nowadays to get a few minutes to yourself where your brain isn't switched on in one way or another. Even if you're just scrolling Instagram or something, you're still taking in content and you're not allowing your mind to, I guess, relax and process the things that it's previously taken in, which I think is quite detrimental. And it also, personally, it's taken a toll on it takes a toll on people's ability to focus on a task, which is something you really need if you want to solve a difficult problem. You need to be able to go to a place in your mind where you can intensely focus on this and channel that sort of creative energy. And that's very detrimental. So when I'm trying to seriously work on something, I try to remove all of these distractions, make it very difficult for myself to access these sort of distractions, um, because your brain doesn't care. Your brain wants that little hit of dopamine whenever it can get it. So I think you need to be very
And I,
mindful of the consequences of that and
mm,
try to put yourself into situations where it's not going to negatively impact your work. And that's the case in any situation.
that's right. Uh, you very rightly said it is something that probably everybody in this generation is being so sensitized to that many of us don't even realize how much time we spend just distracting ourselves from the actual situation and problem at hand.
Oh, it's horrible, yeah. It's very easy to lose track of time.
Because I mean, it's obviously better to scroll on Instagram or YouTube feed for 6 hours straight without realizing how much time you spent, rather than sitting with a math problem or a physics problem for 6 hours or even 3 hours, half the time.
It's a lot easier to do that um, because it expends mental energy sitting with a maths or physics problem for 3 or 6 hours. It spends a lot of mental energy, and you're exhausted by the end of it.
Coming back to what we were talking about, in the quantum realm of things, there the main sort of idea is about the measurement of different possibilities that can occur and sort of choosing the most viable one in its essence. And that straight up leads to the thought trail about many worlds or the entire concept of multiverse. What basis does it have in a very scientific sense, and is there any math to back it up? If there is, what it is?
People often use the word theory interchangeably in a lot of different contexts. In a formal sense, a theory is something that has been rigorously tested over and over again, like Einstein's theory of relativity. When you hear people refer to like theory, multiverse theory, or something like that, or many worlds theory, this is the nomenclature is not quite correct. It's conjecture. There isn't really there isn't any sort of mathematical background supporting any of these ideas. It's sort of just conjecture that some people have come up with. It's more so on the side of science fiction more than anything at this point.
Also, when we talk about scaling quantum systems, or in your area of expertise, scaling the effects of quantum phenomena, quantum biology attempts to understand quantum phenomena and quantum mechanics in regards to physical systems, may it be photosynthesis or the avian navigation in birds, or even the human biology. Are you in any way, have you studied about this to any degree? And if yes, then how does this relate to our interaction with the quantum phenomena?
I don't know very much about quantum biology, but I have heard that there are people working in that sort of direction. I'd be very interested to see exactly what they're doing. I know that there have been some people have been able to perform very simple experiments, uh, testing the quantum effects of, say, small molecules rather than just individual particles. But the problem is, the larger your system is, so like the larger your particle is, the larger your molecule is, the further away from the quantum description you become. So quantum physics describes the behavior of very, very small particles, whereas a molecule is, quite a, compared to like an electron, say, or a quark, it's a very macroscopic object. It's many, many orders of magnitude larger than that. And so at that point, the effects of quantum physics are extremely suppressed, and it's mostly described by a classical description. And of course, I think the purpose of a lot of these experiments is to study small quantum corrections onto this classical description. But as I said before, like quantum physics describes the things that are extremely small. So on a very large macroscopic scales, like the human body, for instance, the any sort of effects are going to be completely, well, I naively say this, completely negligible. I don't know how the brain works. I don't think neuroscientists know how the brain works completely. And so there could be some wacky ideas from quantum mechanics that come into play there. But off the top of my head, I would say that it's probably not what people are thinking it's about. Best guess would be it has something to do with transmission of information through these neural pathways. I'm not quite sure.
A little while back, you talked about the memory effect, or the sort of capability of gravity to attain or retain information to whatever extent possible. And I understand that we are in a very initial phase of this entire research, but probably sometime in future, probably or possibly utilizing gravitational waves as a source of information transmission, could it be viable? Firstly, second, would it have any inherent advantages to do so?
Would it have any inherent what? Sorry.
Advantages to even go down the route of this gravity information transmission sort of.
Well, the memory effect doesn't actually refer to. There's no sort of, in a formal sense of the word information, the memory effect, the physical observable part of the memory effect, so the drift of these two particles from each other when the gravitational wave hits them, that itself does not, that you can't extract any information from that drift itself. The memory effect is intimately tied to information, quantum information, and information in general relativity, although it's interpreted in a much more complicated way and doesn't have anything to do with the, it doesn't really have anything to do with the thing that you can actually measure, which is the separation of these two particles. Off the top of my head, using harnessing gravitational energy as a technology is probably centuries away and minimum. And I'm not quite sure exactly what you would even begin to be able to use this for. It's a similar thing to the electron. Like, we've discovered these things called gravitational waves, but we don't really know how they're going to be technologically useful in the future. Kind of have to wait and see, and hopefully stumble in the right direction enough times to actually come up with something useful. I think in science fiction, there's some sort of gravitational propulsion devices. It would be interesting to explore those sort of ideas. There's actually, you'd be surprised, there's a lot of things from science fiction that have actually inspired real technologies.
And one of those things is one of those things which we are currently realizing in real life is how quick and fast we are scaling artificial intelligence. And do you think that because there are it's assumed that AI will have reached we'll have created and reached the super intelligence level of artificial intelligence in a few decades, if not less. Do you think achieving the zenith in that technology be able to help us to exponentially grow the pace at which we are able to advance in other fields like this one?
I think in the more immediate future, so the next couple of decades, we'll see a lot more AI and artificial intelligence, sorry, AI and like machine learning, which is already partially being used, but being used to a much greater extent in things like data analysis, rather than trying to come up with the more creative, boundary pushing ideas that advance the field. If at some point in time we are able to use artificial intelligence to generate some of these creative ideas, then that would be a really interesting and pivotal moment in science. Something that is completely new to everyone. And if it could do that, then it could come up with ideas and solve potential problems that haven't been able to be solved by conventional means, by people coming up with new ideas. I'm not, I'm not very well versed in the field of AI and machine learning, so this might be a little bit naive. But I don't know. Personally, I don't really think that we'll ever take away that sort of human creative drive that we need to advance these fields. We'll more so use these technologies for the other stuff, like the data analysis stuff, the things that we just you do need a lot of like pattern recognition for these sort of things, which is where like AI and machine learning is very useful, I believe.
I'll probably even paraphrase the question a bit. You're a theoretical physicist, right? You're a physicist. If you were to have a completely realized AI assistant, like when talking about the time when we have achieved super intelligence, right? You have an AI assistant at your disposal that can probably do each and everything that we think of doing with the current AI models. How would you personally utilize the AI system to enhance your prolificacy with your research work?
That's a really great question, and something that came to my mind immediately was trying to understand the connections between lots of different fields within, I guess, mostly physics and mathematics, because that's the sort of area that I'm working in. Use that sort of technology to try to link different ideas that may not have been linked before. The gravitational memory effect, for instance, is intimately related to uh, something called the asymptotic behavior of general relativity, which is essentially the physics that occurs infinitely far away from where you are. It's very intimately tied to that. And both of these ideas, memory effects and also the asymptotic structure of general relativity, had been studied in quite a lot of detail, maybe concurrently to each other, I don't quite remember, but around the same time as each other. And it wasn't until quite recently that people were able to link those two ideas together. So I think it would be very useful for things like that, where you can link existing ideas together that haven't necessarily been linked before, because it gives you a much richer understanding of the things that we already do know.
Also, somebody who's just getting into this area or just starting out, a young physicist, what would your advice be? Or sort of, firstly, what would you suggest as a roadmap for an aspiring physicist in any subfield to approach research and development with? And secondly, what is your advice for them, a general advice for them to continue to do so?
I think a good piece of advice, and this is not just in physics or science, any field, any person, follow your curiosity if you have the means. It's a fantastic thing to do. But in the context of science and physics specifically, going down the academic route is a relatively linear path. You do a bachelor's degree, depending on what part of the world you're in, you do a master's degree or not, and then you move into a PhD, and then you do postdocs until you get some sort of permanent position at a university or research institution. Or at that point, some people also move into industry, where they're dealing with more practical applications of the science that they understand. So it is relatively linear in that sense. Um, but I will also say, from my well, academia is not for everyone. It's pretty cutthroat. It's a lot of the time it's really not easy. The research bit is the fun bit. Dealing with funding and bureaucracy, all of that kind of thing, logistics, that's the difficult bit. And that's the bit that kicks a lot of people out of research. And so I guess, yes, go into it being curious and passionate about whatever you want to study, whatever you want to learn about, but don't be so discouraged if it's not the path that you end up down. Most people that I know who started in physics or in science degrees are not in academia anymore. And I mean, part of that is scientists are very useful outside of academia, within tech and politics and various other fields as well. We need people who are trained as scientists working in these fields. It's very useful, which is why they're highly sought after. Um, yeah, going down the academic route is not the be all and end all of things. There are plenty of other ways you can do great research, great innovation, without going down this extremely narrow linear academic route.
My immediate follow-up question to that would be, for someone who just wants to pursue academia, how should they survive and thrive in it?
Don't be afraid to look stupid. People, myself included, at different points in time, are afraid to look stupid amongst their peers and amongst people above them academically. It's like professors or tutors, things like that. And so they don't ask the questions that you need to ask to really learn about a field or a subject, anything. And it's that naivety that actually, I guess it's the admission and acknowledgement of that naivety that actually allows you to learn and progress within a field. Not necessarily science, but anything. And I think that has been probably one of the most important things that I have learned uh, throughout my academic career so far, is that you sometimes need to be the stupid person in the room, ask stupid questions, because yeah, sometimes they are stupid questions, but other times they're not stupid questions and they make other people think about their own understanding.
Or for somebody who probably wants to do both, they want to pursue thorough pure sciences research side of things, but then also transition into or follow the corporate side of things. They're taking a transition, doing their PhD, and then going and working in the for corporate organizations. Do you have any advice on how do they make that shift from research to the application field, or vice versa? For somebody who's been working in the industry and they realize, oh, I want to pursue academy or research, how do they make a transition?
First of all, to answer your second question, I think to transition from academia to field and industry, if you're rather experienced in your field and your field has a fairly significant technological component, say, then I don't think it'd be that difficult to progress, to transition from academia into industry, because there's probably already an industry built around the kind of things that you're working on. But from what I've seen from all the people around me and some of the things that I've done, going from the academic route to industry, or working in a large company or something like that, or even just like a startup, a lot of it is networking. A lot of it is putting yourself out there and showing other people your skills. So doing a lot of talks, podcasts like this, industry networking events, and sort of extracurricular activities that you can get involved with that'll give you connections in these sort of industry fields that you want to potentially go into, just to develop contacts and get your foot in the door a little bit, is extremely useful. It's much more useful than just cold applying to a bunch of different positions.
What would you recommend, pursuing a PhD straight after bachelor's or doing the master's? What are the pros and cons of both the approaches?
Okay, I mean, that's highly dependent on where you are in the world. In like continental Europe, it's very common for people. It's a standard for people to do a 3-year bachelor's and then a master's for like a year or two, and then you go into a PhD program from there. And most PhD programs won't admit you without most PhD programs in Europe won't admit you without a master's degree. In Australia, it's a little bit different, at least within the sciences. I can't speak on other fields, but it's extremely uncommon for someone to do a master's degree in a scientific field. We do a 4-year bachelor's, and then we go straight into a PhD program, which is about 4 years. And the PhD program over here in like Switzerland and other parts of Europe is about the same, between 3 and 4 years. However, if you go to the United States, for instance, their tertiary education system is a little bit different. They usually do, well, I'm not quite sure how long their bachelor's degrees usually are. I think between like 3 and 5 years, something like that. And then they also go straight into a PhD, except the average time the average duration of the PhD from an institution in the United States is between like 4 and 6 years, something like that. I think the average is closer to 5 or 6, and that's because they do a lot of they, they do kind of an integrated masters within their PhD as well. They do a lot of coursework in the first couple of years before they even jump into like the meat of the research. Um, Whereas I think that's, I mean, to my knowledge at least, it's the only part of the world where they do this sort of integrated PhD master's program, but like call it the same thing.
As my final question to you, how do you think, what state of world would we be in a decade or two from now, and the scientific aspect of things, where theoretical physics and such fields would be standing from a decade or two from now?
A decade or two from now, it's fun to think about. In the context of my own work, I think there will be a much larger emphasis on probably a lot more people moving towards like gravitational wave physics and early universe physics, which is actually something that I'll be working on during my PhD in the field of early universe physics, because like this LISA gravitational wave detector that I mentioned before is going to be able to measure some. It's predicted to be able to measure some effects, gravitational wave effects from the very very early universe, which will be able to use, which we will be able to use as a probe to study the physics that happened in the very turbulent and early stages of when our universe is forming. And so I think there already are a lot of people moving in that direction in Australia, in Europe, and there's a few people in the States as well doing that. I'm not sure about other parts of the world. Um, so I think there'll be a lot more of that, much more people working in the field of gravitational physics. Um, it already was booming and growing rapidly with the discovery of the gravitational waves from LIGO. So in the few decades before that, it was already growing quite rapidly, and I think we'll see that similar sort of growth in the next couple of decades in that field. I also think, and we talked about this before, there'll be more of an emphasis on machine learning and maybe artificial intelligence as well in fields like particle physics and other fields where there's a lot of data analysis or very computationally heavy calculations that need to be done, because that sort of thing is very useful in that area. Um, yeah, I think we are slowly stepping away, and I'm not sure if this is a good thing, a bad thing, or neutral, but we are slowly stepping away from the more highly theoretical fields, at least in physics. If you go back to mid 20th century to late 20th century, for instance, a lot of theoretical physics was purely pen and paper stuff. So you'd write down an equation, try to solve something, you'd publish your result, and that was it. Nowadays, there's a much heavier emphasis on the computational side of things in theoretical physics, just because we've got these great big experiments like CERN and gravitational wave detectors that are producing enormous amount of data that we have to filter through, analyze, and try to find meaningful things in that. And there's still plenty of data from LIGO and from CERN that we're yet to filter through. And with things like machine learning, we're going to be able to filter through those much more quickly, much more effectively, to discover things that haven't been discovered yet. And so, yeah, I do think we're moving further away from the more pen and paper stuff. I don't know if that will be permanent or not. It'll be interesting to see.
There's this final segment in the show that we have currently been inducing, which is, what is your word for humanity at large?
What is my word for humanity?
At large, yes.
I guess don't discount the usefulness of being playful and curious and creative in your work, no matter what it is. I mean, at the end of the day, we're here for a finite time, so may as well have fun with it.
Mr. Flynn Linton, it was a pleasure talking to you.
Thanks for having me. I really appreciate it. This is a lot of fun.